Welcome to this preview of what you will learn from using modern database management in your course. Hi, I'm Jeff Hoffer, one of the co-authors of Modern Database Management. In this tutorial, you will be introduced to databases. We'll do this through a series of questions about databases and with examples of the use of a sample database. We will cover what is a database, what are the components of a database, what do we do with a database, and in this section we'll work with some simple database query examples. What is the most common way of thinking about a database? Are there different kinds of databases? What technology do we use to access a database? And here we'll work with some more advanced query examples. And finally, how can I write some simple queries now? So, what is a database? Consider data about your university library. The library staff would want to know data about books, magazines, and DVDs that the library has in its holdings, about students who use the library, and about the checkout of holdings by students. This data won't be very accessible if it is haphazardly managed. The data will be easier to retrieve, maintain, and protect if we organize the data into similar collections first. For example, all the books, DVDs, and magazines into one collection, and then all the students into another collection, and finally all of the checkout slips into a third collection of all these various logically related items, hence a database. In this example, checkout slips help us logically relate students to the books, magazines, and DVDs they use. Also, we even group different items, books, magazines, and DVDs, into one supercategory of all of the library's holdings. This picture makes it easier to understand what data we have about the library and even suggests, as we will see, how we might find logically related items. More on this later. From this library example, you probably have an intuitive feel for the components of a database. Let's look at another example to identify the components there. First, there are entities, such as persons, in this case customers, objects, here we have products, events, customers placing orders, and concepts, the line items on orders, which might represent data we need to help run a product manufacturing company. Second, each of these entities has characteristics that describe them, which we call attributes, such as name and address for customers, description and finish for products, order date for orders, and ordered quantity for the line items. And there are special attributes, called identifiers, that uniquely distinguish, for example, each customer from every other customer. For simplicity, we'll call these Customer ID, Product ID, and Order ID. Each order line item, which represents how much of a given product was ordered on each order, will be identified by a combination of Order ID and Product ID. We'll come back to this question of components of a database in a moment, but let's first think about what do we do with a database. Actually, there is much that we can do, but before we can talk about that, we have to have a more workable way to visualize data in the database. Today, this is done by thinking of each entity as a table of data. For example, consider what we show here, the product table. This product table will have a different column for each product attribute and a different row for each product we sell. A basic task is to simply search a table for data we need. To do this, we need to query the table using a query language, just as we might ask a reference librarian to find resources we need to write a research paper. For databases, there is an international standard language called SQL or SQL that we can use with almost all databases. So, using the SQL language, we can write questions about the data in the product table, such as what are the product finishes? What are the distinct product finishes? what products are made of ash, and how many products are made of ash. Now, let's see how we would do this using database software. Because of its ease of use and availability via the internet, we'll use SQL Assistant Web Edition from Teradata, a leading supplier of very high performance database software. We are accessing this software via Teradata Student Network. You can read about TSN on the inside front cover of the textbook. Now, I've simplified the SQL Assistant screen so we can concentrate just on the SQL commands we will enter and the results. Using the SQL language, we're going to query a table of data about products in a fictitious company called Pine Valley Furniture. The first question we just asked is one of the simplest kinds of questions, which is to see the values of some attribute. You'll remember this question was, what are the product finishes? The SQL command to show data in a table is select. And we need to include with the select command the name of the table where the data is stored, in this case product T. And the name of the attribute we want to display, in this case product finish. So the command is fairly simple. It is select product finish, which is the attribute we want to display, from product underscore T, which is the name of the table where we find the attribute we want to display. We end each SQL command with a semicolon. And then we click the Execute button to see the result or answer set. SQL shows the result of queries in a table of values. So SQL, being a relational database language, is perfectly consistent. It stores raw data as tables and produces results as tables. This is convenient in case we ever want to store the result of a query back into the database or use the result of one query as a table in another query. That's when SQL really gets powerful. Looking at the result of our query, we don't need to see the same product finish values repeated. So our next question was, what are the distinct product finishes? To answer this, we can edit the previous query by inserting the SQL keyword distinct in front of the attribute we want to display. So we get select distinct product finish from product underscore T. Now when we click the Execute button, we don't see product finish values repeated. Another frequent question is to find a row in a table, in this case rows for different products, that have some common characteristic. You'll remember that we said we could ask the database just this kind of question, which was, what products are made of ash? Looking at the result of this last query, we see that a value of finish is natural ash, not just ash. We'll need to be very precise then with our query. So we need to place a qualification on the rows we want to display. In this case, we want to see all the attributes of the natural ash products. We could list all the names of the attributes of product after select, just like we listed product finish before, but we'll use a shortcut. In our select, we'll replace distinct product finish with a wildcard symbol of asterisk. Meaning all of the attributes. Then we need to limit the rows to qualify and display data with the where clause. So we'll add to our query where product finish equals natural ash. We have to put single quote marks around natural ash because SQL sees it as a string of characters, and space is a legitimate character. So we need the quote marks to say where the phrase we want to search on begins and ends. Now, when we click the Execute button, we see data from all the attributes or columns of the product table, But notice that we see rows where the value of finish is only natural ash, which is what we asked for. The final example question we discussed earlier was a little different. That question was, how many products are made of natural ash? So sometimes we don't actually have to see the raw data, but rather want to aggregate the data in some way, letting SQL compute that summary for us. In other words, we want to count the number of rows in the product table where finish is natural ash. This means we can edit our previous SQL command to display a count rather than the attribute values. So we are going to replace asterisk with count asterisk. Here the asterisk tells the count function to count the rows. Then when we click the execute button, we still see a table, but this time the table has just a column heading and one row with the count. Well, we have our result, but it's not very pretty. Thankfully, SQL gives us an ability to reformat answer tables. In this case, let's rename the count to be how many ash, which we can do by editing our query by inserting an alias with this name after the count function. Then when we click the execute button, we get the same result as before, but with a more readable column heading. Now, let's return to the discussion of databases to see how to connect logically related data. You'll recall that we said a database was not only an organized collection, but also said that it was a collection of logically related parts. By logically related, we mean there are associations between the data. Remember how students and library holdings were associated in our prior example. What we need then is a special type of glue to hold the related parts of the database together. This glue allows us to take paths through the database going from one related part to another so that we can store data in only one place, thus minimizing the chance of errors. These linkages between data are called relationships. Let's see some examples. Customers and orders are related because a customer places an order. Orders and line items are related because an order includes a number of line items. Products and line items are related because products are included on a number of line items. Are customers and products related? Well, sure they are, but this is an implicit relationship because customers place orders which include line items which have products included on them. The relationship glue allows us to walk a number of relationship paths to find associated data. Neat, huh? Okay, this is a nice picture, but is there a better, more functional way to think about databases? Of course there is. Let's consider two of the entities in our example database, customers and orders. You'll remember that a good way to represent each of these entities is via a table. So here are two sample tables with rows for each customer and order, and columns for some of the attributes of customers and orders. What we are missing so far is a way to represent the relationship, places, between customers and orders. If there were only some piece of data that would tell us for each order who was the customer who placed that order. Well, we already know such an attribute. It's customer ID. So let's add customer ID with its data to the order table, along with the other order data. Each order has only one customer, and hence only one customer ID. So we can easily add this data to the table. Now, because we have customer ID in both tables, what we call a common column, we can relate each order to the associated customer. So, order 40 is for customer 2, order 42 is also for customer 2, and order 41 is for customer 3. We don't have to put other customer data, like customer name, in each order row because we can find it by taking the path for the places relationship. Taking these relationship paths is called joining in database terminology. The technical term for the customer ID attribute in the order table is a foreign key. You can think of it as a cross-reference. What we see here are the main characteristics of the most common way of thinking about a database, the relational database model. So, what makes the relational database model so special? In short, simplicity and parsimony. Let's see why. You might think, wouldn't it be easier if we put all the data we need into one table, rather than splitting the data into two tables? Well, what happens? First, we have redundancy, and usually extra space consumed because repeated data are usually the largest pieces of data. And we might have errors. We can't ensure that the same customer data, for example the address for Amber, are entered with the same value each time. And we might have anomalies or inconsistencies, such as where would we store data about customers who don't have any orders? For example, customer 1. Where would we store data about customers whose last order is deleted? For example, order 41 in customer 3. Which customer order data must change when there is a change to customer data? For example, all orders for customer 2. And we need to check that customer 8 really exists, so there must be a cross-reference. But we don't lose anything when we have two tables, because we can find the related data via the cross-reference. We'll illustrate this later in some sample queries. Actually, we can build a wide variety of databases using the relational database model. Although the fundamental principles are the same, they look a little different. We can build databases to run the operations of the business, such as order entry and accounting. We can build analytical databases to support decision-making, such as market segmentation and sales forecasting. We can build complex network-like structures of hundreds of tables, or simpler structures that look like stars or even cubes. You can think of a pivot table from Microsoft Excel. We can even build hierarchical structures that allow us to relate customers, for example, to their geography of city, state, and country, which allows us to find data at different levels of aggregation. Pretty powerful, huh? With this powerful concept of relational databases, we need powerful technology to help us access and manage the database. This technology is called a database management system, or DBMS. A DBMS helps us to protect data by, for example, ensuring authorized use via user IDs and passwords and putting integrity controls on data. To define tables and control performance of the database by applying very technical structures and backing up the database in case the primary copy of data is damaged in some way. To maintain data, which allows us to enter, change, and delete database contents. To retrieve data, which will likely be the bulk of the activity against any database. And to do all of these things either through a programming language like SQL, either by itself or within another more general purpose programming language like Java, or with the help of a more friendly graphical user interface like Teradata SQL Assistant, which we saw earlier. Let's see some more examples of using a database, but this time we'll do more complex queries involving data from more than one table, thus taking advantage of the relationship glue that allows us to find related data in a database. Here is our Pine Valley Furniture Company database about customers, their orders, products, and the line items, showing the quantity ordered for each product on an order. Suppose we wanted to know the names of customers, along with the dates and order IDs of all their orders, in sequence by customer names and order dates within name. This query involves data from the customer and order tables. You'll recall the places relationship that links customers with their orders. You may also recall that we showed that the places relationship was implemented in the database by a cross-reference. That is, a customer ID is stored in each row of the order table. This customer ID cross-reference is a foreign key that links each order row to its associated customer. Now, we have a pretty good idea what our query will have to do. We want to show or select customer name, order date, and order ID. Somehow tell SQL to match the customer ID in an order with the customer ID in a customer row so we can find the name of the customer for that order. And let's show these in sequence by customer names and order dates within name so the display will be easier to understand. We're using Teradata SQL Assistant Web Edition again, as we did with the previous SQL queries. Compared to when we used SQL Assistant before, this time we see some additional elements of the SQL Assistant Web Edition interface. On the left, I have expanded what is called the directory tree, so that we can see the names of all the tables in the database and all the columns in the two tables, customer and order, we need for the first query we're going to write. This is reference information, or what is called metadata, to remind us of the correct names of tables and attributes to use in the queries. Also showing in the middle of the screen this time is the history pane. Each time I enter a SQL command, that statement goes into the history, and I can recall it into the query panel at any time to help me write another query. Usually, history persists for each user, but I've cleared out the history of commands I've previously entered to make our screen less busy to start. Now for our query. Remember, what we wanted to do is to list the names of customers along with the dates and order IDs of all their orders, showing these in sequence by customer names and then order dates within name. To show the customer name and order date and ID, we put these into a select statement. Because these attributes come from two tables, customer and order, we have to list both of these tables in the from clause. Now for the new part. We have to tell SQL how to find the row in the customer table that matches each row of the order table. Recall, this is our foreign key of customer ID that is found in both tables. So here's customer ID in the customer table and the foreign key of customer ID in the order table. So we have a qualification. We want to match an order row with the customer row that has the same value of customer ID. We do this in a where clause. We had to tell SQL where to find each customer ID. So we prefaced each customer ID with the name of the table we wanted to use. The final part of our query imposes an output sequence of first by customer name and then by order date, which happens to be the first and second attributes in our select command. So we can add to our query which tells SQL to arrange the data in the sequence we desire. We could have said order by customer name, comma, order date, but wasn't it easier to just use the column position numbers? We then click the execute button to get the result. The critical element of what we just did was to know that customer ID is a common attribute or column in both tables, and that we can find matching values to join customer data to order data without having to repeat customer data in every order. In our next SQL example, we want to know the product description and its total amount ordered for each product Pine Valley Furniture Company has sold. So this time we need data from the product and line item tables. You may also recall that we showed that the included on relationship linked product with line item, and this relationship was implemented in the database by a cross-reference. That is, the associated product ID is stored in each row of the line item table. This product ID cross-reference is a foreign key that links each line item row to its associated product. Now we have a general idea what our query will have to do. We want to show or select product description along with a total or sum of all the ordered quantities in line items for each product. And somehow we'll have to tell SQL to sum up the right ordered rows. But from our last query, we should have a pretty good idea how to tell SQL to match a row in the line item table with its associated product. We'll begin with select and the attributes we want to display. The first attribute is product description. So we enter select product description. Then we want a total. SQL has a variety of functions to help us aggregate data, like the count function we used earlier. And the function we need this time is sum. So we enter sum and include in parentheses the name of the attribute we want to total. So we'll enter sum, and that attribute is ordered quantity. As always, we have to tell SQL where to find the data. And in this case, there are two tables involved, from the product table and the order line table. Because we are using data from these two tables, we need to join them together on their common column, which in this case is product ID. As before, we'll use a where clause to do this. So we enter where, and we'll tell SQL where to find the data. So the first product ID is from the order line table. And we'll match that with from the product table, the product ID. Now we have one part of the query remaining. In our select, we ask SQL to compute a sum of the ordered quantity values. We don't want a total across all order line items. Rather, we want this done separately for each product description. In other words, we want SQL to group the line items by product description and then give us a separate subtotal for each. We do this with the clause group by, and we tell which column to group by. In this case, the first column or product description. Then we click the execute button. We see the results we desire, which is a table of product descriptions with the subtotal of the quantity ordered next to each. This will be our last example and the most complex of the ones we'll show. The query is, who are all the customers who have bought any product called a computer desk? This query is asking us to link products to the customers who have bought them. But, as we noted earlier, we don't have a direct relationship from product to customer. Don't worry. Rather, we can get from product to customer through line item to order and finally to customer. So, now we also need the includes relationship and the foreign key of order ID from line item to order. And we'll need to limit our search to only products with a description of computer desk. Let's see what we need to do in SQL to accomplish this. The query asks for a single column to be displayed. So our select clause is simply select distinct customer name. We use distinct because the same customer may have bought several computer desks. Now, even though we are displaying data from only one table, the customer table, We realize we are interested in only certain products, those with a description of computer desk. So we'll need a where clause of where product description is computer desk. Thus, we need data, product description, from also the product table. In addition, as we discussed when looking at the diagram of the database, we have to match a computer desk with the line items it's included on, and then each line item with its order, and finally find the customer for that order. So we actually need all four tables to follow the relationship path from product to customer. Hence our from clause is from the product table, the order line table, the order table, and the customer table. Notice I've included an alias with each table name. You'll see in a moment that this will save some typing as we write the rest of the query. What is left to do is the matching of tables, which as before we do with where clauses to join tables based upon their common attributes. We join each pair of tables, and we'll just add another component to the where clause we've already entered for each pair of tables we need to join. So let's start with matching product with line item via the common column of product ID. See how I used the aliases so I didn't have to type in the whole table name this time? Then I'll continue with the other two joins. And I'll click the execute button to find the customer or customers who have bought computer desks. Now that you've seen some examples, you might want to try to write some SQL queries yourself. Here's how. If you look at the inside front cover of the textbook, you'll see how to access the database that we've used in this video. Versions of this database using a variety of database management systems are provided on the textbook's website. The database is also preloaded on Teradata University Network, and here are links for faculty and students to use Teradata University and student networks. On the home page, if you look for SQL Assistant Trial under the Access Content on the home page, you'll be able to use the same interface that we've used for the Pine Valley Furniture Company database. This database is also preloaded and accessible after faculty register your course in this database for student use. In this way, you can use a lot more functionality than we are able to use with the trial version. And see Teradata University Network for details on this. If you want to practice writing SQL, this screen presents some questions you could answer with SQL from our example database.